Hey there, welcome to our discussion on expected value or expectation. This discussion will be valuable for trying to figure out if a certain venture is worth it or not, whether it be business or a gambling game or just figuring out whether you want to hold that garage sale on Saturday or not due to the weather. Expected value can help you figure that out. Because what expected value does is it gives you the amount you can expect to lose or gain on average over the long haul. Um, you really, it doesn't give you enough information about a specific instance, such as, what's going to happen specifically on Saturday at 1 o'clock. But what you can look at is what happens on average over lots of days or over lots of instances, and then use that average to make an intelligent decision about whether something's worth it or not. Like in the case of a business venture, you know, on average, do you expect to gain or lose? If you expect to lose on average, then it's probably not worth the risk. If you expect to gain on average, then it might be worth the risk. You'll have to see how much you expect to gain and decide for yourself. A lot of things are risks, and you can't necessarily say for sure what will happen. But having information about averages can at least help you make an informed, intelligent decision. Okay, so how is expected value, or also called expectation, how is it found? Really, it's a basic formula. Uh, the formula looks long and complicated here, but what it's saying is whatever your possible outcomes are to the situation, you take each outcome, you take the probability of it occurring times the amount you stand to gain or lose. If you expect to gain, then it's positive. If you start to lose, then it's negative. And if you only have two possible outcomes, then you're only going to do, you're going to do this probability times the amount twice and add up the results. You just keep however many you have to work with. You multiply your probability times the amount you stand to gain or lose, and then add them all up. And then that'll give you your expectation. All right. So rather than staring at that formula there, let's take a look at an example. All right. Let's say that you have a proposed business venture. I'm pulling this right out of the book, by the way. It's number 7 in the current textbook. So proposed business venture, and there's a 60% chance to make $80,000. And then there's a 40% chance to lose $20,000. I'm already looking at this. Looks like it's going to be a positive expectation. Just looking at the probabilities and the amounts that are involved. It says determine the expected value. So there's a gal named Stephanie who's looking at, analyzing this proposed business venture, trying to make a decision about whether to take the leap and take the risk. So finding the expectation can help her make a decision on whether it's worth taking that risk or not. So to find the expectation, we're going to have to look at probability of making money times the amount she would make, plus the probability of losing money times the amount she would lose. Okay, and this will give us on average what would happen if she opened a ton of these businesses. Okay, so 60% chance to make $80,000. Let's go ahead and use the decimal form of 60%. Remember, 60% is the same thing as 0.6 or 0.60, and 40% is the same thing as 0.40. So 0.6 times 80,000, because she would make 80,000. It doesn't say anything about how much she's invested, so it's saying just outright she would make $80,000. Plus, we have to look at 40% chance to lose. So 0.4 times, and then losing 20,000 is a negative. Because that money would be, if you're losing it, that's a minus. So you got 0.6 times positive 80,000, which will give you 48,000. And 0.4 times negative 20,000, which would give you negative 8,000. Combine the two, 48,000 minus 8,000, and you get 40,000. And we're dealing with money, so it's dollars. Okay, so that's her expectation. So on this one business venture, she's either going to make 80,000 or lose 20,000. In that one single instance, that's what's going to happen. But when she's trying to make her decision about whether to risk it or not, knowing that on average these business ventures come out $40,000 in the black, can let her know, hey, this isn't, the risk isn't too bad. So on average, this venture makes $40,000. So if you if you look at a ton of people who've done that same business venture, there's going to be some that made 80,000, some that lost 20,000. More of them made 80,000, fewer of them lost 20,000, so it averages out to profits of $40,000. Or this could be help you make an intelligent decision too over, do I want to open, like, let's say it's a chain of restaurants. Maybe the business venture is a chain. And if you know that on average each restaurant would make about $40,000, you can be like, okay, I'll open a bunch of them. Yes, some of them will lose, but more of them will gain, and that'll make it worth my while. So that's the kind of thinking you can apply to this. It's still probability. You have no way of knowing for sure what's going to happen in the future. But you can do your best to take the appropriate risks. All right, another one. Investment club purchasing stock. This is actually number 11 in the book. All right, with that in mind, there's a 70% chance of making $15,000. A 10% chance of breaking even. And then a 20% chance of losing $8,500. So we want to determine the expectation of this stock purchase. Well, breaking even is exactly what it sounds like. You're coming out at $0. You neither gain nor lose in the end if you break even. So pretty good chances of making some money, but there is still a chance too of losing money or breaking even. So we got to figure out this expectation. We're going to do probability times amount for making money, plus we're going to do probability times amount for breaking even, plus we're going to do probability times amount for losing money. Okay, so making money, 70% chance, that's 0.7, and then you would make $15,000. Breaking even is a 10% chance, that's 0.1 times $0. And then losing money is a 20% chance, so 0.2, and then you're losing, so negative $8,500. So let's see what we have here. 0.7 times 15,000. We're going to get 0, 0, 35, 10. We're going to have positive 10,500 on that one. Anything times 0 is 0 on that breaking even one. And then we're going to have negative 0, 10, 16, 17. Negative $1,700 on the losing one. So you combine all that, and what do you end up with? I'm getting $8,800 as my expectation. Okay, so you buy a bunch of shares of this stock. 70% chance of making 15,000, 10% chance of breaking even, 20% chance of losing 8,500. If you make it a risk like this over lots of stocks, same risk, then on average you can expect each stock to come out $8,800 ahead. Even though some will break even, some will lose, some will make 15,000. This is just giving you a picture of what happens in the long run, or if you do multiple trials of something. Like, not purchase necessarily the same company stock, but if you purchase a bunch of shares of different stocks that have the same values there, same probabilities and amounts, then on average you can expect to come out $8,800 ahead per purchase. So that's not a bad investment. That's not too bad of a risk, really. One stock might be a little risky. One purchase might be a little risky, but maybe several wouldn't be so much. All right. Mike and Dave play the following game. Okay. Mike picks a card from a deck. And we're just using our standard deck that we've been working with. 52 cards. If an ace, Dave gives him $5. Okay. If not, he gives Dave $2. All right, let's first figure out Mike's expectation. By the way, this is number 14 in the current book. Okay, so Mike picks a card from a deck. If he has the probability of an ace, whatever that is, he will gain $5. But probability of not an ace, he will lose $2. Okay, so think about a standard 52 card deck. We have what, 4 aces in there? Because we have the ace of spades, ace of hearts, ace of diamonds, and ace of clubs. So there's 4 aces out of 52 cards in a standard deck. So probability of grabbing an ace, if you're just picking any card from a standard 52 card deck, is 4 over 52, or 1 over 13. And I'm going to multiply that by 5. So 1 over 13, you're going to end up with 5/13. And we'll convert that to dollars in a minute. Probability of not an ace would be the fact that there's 48 cards that are not aces, because you can just do 1 minus 4 over 52. 48 cards that are not aces out of 52 cards, times that negative $2. Well, if you have 1/13 here, that's 12/13 times 2 is going to be 24/13. So minus 24/13. So you end up with negative 19/13, whatever that comes out to. Now we are dealing with money, so let's go ahead and quickly put that in a calculator and see what that comes out to. 19 divided by 13, and I get 1.461538462. So about $1.46. So this does not sound like a very good game for Mike to play, because he has a low probability of getting the $5 and a high probability of losing $2. So on average, if he plays this game a lot of times with Dave, on average he's going to lose $1.46. So not a good game for Mike to play. But if Mike plays a bunch of times and on average loses $1.46, remember he's paying that $1.46 to Dave. Dave's expectation is the opposite number, positive $1.46. So if they play this game hundreds of times, Dave on average is going to be making $1.46 per play. So this is a very good game for Dave. So Dave would benefit from playing this game lots of times. Mike, not so much. But there you go. That's the expectation. Now, when we're talking about expectation, there's another thing we can talk about called fair price. The fair price of a game or other venture is if you decided, you know what, if somebody plays my game hundreds of times, I want them to break even in the long run. So the fair price is what you would charge them to play if you want them to break even overall. They won't break even on each individual play, but if they sat there and played a lot. Like let's say you're doing a slot machine and you're like, well, each time you play, you're either going to be feeding money or you're going to be winning some money, but if you play hundreds of times, I want you to walk away with how you started. So to find that, if you have a game, you want to find the fair price, you figure out the expectation for the game, and you add that to the current cost to play the game, and the result will be the fair price. Okay, so for example, let's say you have a raffle. And this is number 22 in the current text. All right, we have a raffle with 1,000 tickets being sold. Okay, so in that raffle, tickets are $2 each. One prize of $600. Okay, so there's a gal named Rena who purchases one ticket. Determine her expected value. Okay, so Rena plays. She's either going to win the raffle or she's going to lose the raffle. Okay, so if they're selling 1,000 tickets and she purchases only one ticket, she has one chance out of 1,000 to win this raffle. And if she wins, how much is she going to come out with? And I know it's very tempting to immediately say, oh, she's going to win 600 bucks. Well, it's true that she's going to, if she wins, she will win $600. But what will she actually walk away with? She will actually walk away with $598. Remember, she had to buy a ticket. Like you see somebody who wins the lottery, my question in my mind is always, well, how many tickets did they buy until they won? Because that factors into how much they actually walk away with, not including, taking taxes out and all that loveliness. She walks away with this after buying a ticket and winning. Okay. And then if the probability of winning is 1 over 1,000, the probability of losing is 999 over 1,000. Much greater probability of losing. But hey, it's still fun to play. It's only $1 or only $2. Somebody's got to win. If she loses, she's just out her $2 she played. She bought the ticket with. That's it. She's only out the $2. That's the ticket price. So if she loses, she's not walking away with 0. She's actually walking away with -2 because her wallet's $2 shorter than it was when she came into the got ready to play the game. All right, so expectation, you have 598 over 1,000 minus 1998 over 1,000. This is going to give you -400 over 1,000. Let me erase that little mark because it almost looks like I was about to write a 0 there. I didn't mean to. There we go. Which in terms of money, because remember this is in terms of money with ticket prices and everything and winnings, is -40 cents. Not a real great game for her to play. All right, something's not working out quite right. It looks like it's supposed to be -$1.40. Maybe I did something wrong in my head here. Sorry. All right, so 1,000 tickets, $2 each. So if she wins $600, but she walks away with 598. So you get 598 over 1,000. And then you got $2 for the ticket. I was trying to do too much in my head, I think. 1998. Yep. Minus 598 is, oh, 1,400. That's what happened. Sorry about that. It's a silly mistake. I was subtracting the 5 from the 9, but forgot about that 1 over there. So add a 1 there. Dun, dun, dun. That's a -$1.40. There we go. That makes more sense. Okay, so her expectation is -$1.40. But still, not a great game for her to play. If she bought all 1,000 tickets, she'd be spending $2,000 on tickets and only walking away with $600 in winnings. So she'd be out $1,400 in the long run. So, you know, overall, on average, if you play this raffle a ton of times, you're going to lose $1.40 per play. Which is great for usually raffles are fundraisers for something, like a church or a school or whatever. So they want people on average to lose money because that's their gain for the fundraiser. That's usually how this works. That's how they end up making money on raffles. And a lot of times prizes are donated when it comes to raffles. In this case, they're taking the prize money out of what their ticket sales. So even though they have to give out the prize of $600, they're bringing in $2,000 in ticket sales minus the $600 prize, and they're still walking away with $1,400. And -$1.40 times 1,000 tickets is that $1,400. Okay, fair price. Take that expectation of -$1.40 plus the cost to play, which was $2, and the fair price is 60 cents. So this is what they should charge if they want everybody to break even. If they want to go home at the end of the day with no profit, just $0 profit, and so an overall break even. So if you think about it, the 60 cents per ticket times 1,000 tickets would bring in $600, which they would then immediately pay out to the winner for the prize of $600. So the people running the raffle in that case would not end up raising any funds. They would break even if they sold all 1,000 tickets and gave out $600. So that's not what they're there to do. They're probably there to make some money, so the tickets are higher in cost, like in this case $2 each. All right, let me do one more example with you. Let's see. Let's say we have a spinner. Spinny, spin, spin. Should be a nice circle. Sorry that that's not a perfect circle. I'm doing my best. It's a nice little spinner game. Dang it. I'll do that. Half of the game, if the spinner lands there, it's a $10 prize. A quarter of the game, if the spinner lands there, it's a $1 prize. And the other quarter of a game, it's a $5 prize. See, if you assume that the person spins the pointer and is awarded the amount indicated by the pointer. The cost is $2 per play. So each time you spin it, we're going to assume it doesn't land on the lines. We're going to assume that equally likely chances of it landing anywhere else in the winning slots. So we want to figure out expectation of the player. If the person played this game a ton of times, what would they expect? Well, the probability of landing on the $10 slot is 1/2. But if they landed on the $10 slot, at the end of the day, they would not walk home with $10. They would actually walk home $8 richer because they had to pay $2 to play. For the $5 slot, probability of landing there is 1/4 because it's 1/4 of the circle. They would actually walk away with $3 at the end of the day because they had to pay $2 to play. And then for the $1 slot, probability of landing there is 1/4, and they'd actually walk away negative $1. If they only brought their wallet had to pay out $2, they only got $1 of that back. So they lost $1 basically. So this is for landing on the $10 spot. This is for landing on the $5 spot, and this is for landing on the $1 spot. All right, so half of 8 is $4, plus we got 3/4 of $1 or 75 cents, minus 1/4 of $1 or 25 cents. So 475 minus 25 gives us 450. That's not a bad little game to play then. Play that game a ton of times, you can expect to walk away on average $450 richer per play. So that's not so bad. Now, if you wanted to set the game to have a fair price so that a person could sit there and play and play and play and then walk away breaking even, you take that expectation of $450 plus the $2 it costs to play, and you say, well, the fair price to play would be $650. Or for the person running the game, if they decided they didn't want to win or lose, gain or lose money running the game, they would say, well, let's charge $650 per play. And if they did that, watch what happens to the expectation. It's kind of neat to see what happens when you use your formula. A half times, well, if you charge $650 to play, and the person lands on the $10 slot, they're going to walk away with $350. If you're charging $650 to play and the person lands on the $5 slot, they're going to walk away negative $1.50. And if you're charging $1 to play, or if you're charging $650 to play and the person lands on the $1 slot, they're going to walk away with negative $5.50. So we got what, 1.75 here minus, see, 4 times 3 is 12. 4 times 7 is 28, 7, so it's going to be 38 cents minus 4 times 3 is 12, $1.38. So you work all that out. I should probably not round. I need to just leave it not rounded, because that way we can show that it actually comes out to that 0. Rounding messes things up. I should know better. So what happens there is you actually have 0.375. Where did my pen go? There it is. Here it's actually 0.375. There it's actually 0.375. All right, so $1.75. Well, negative 0.375 and negative 0.375 is a negative $1.75. You combine all that, and you get $0. So that's the fun thing that happens when you charge the fair price. You figure out your expectation using the formula, and you will get $0 if you have the correct fair price. But there you go. So there's 11.3 for you, expectation and fair price. Think about this when you play the lottery. I know I'm guilty. I'm like, oh, if I don't buy a ticket, I'll never win. But if you really start looking at the lottery tickets and the probability of winning, the expectation for you is negative. And that's how the lottery officials make their money. Every ticket's expectation is negative. Yeah, somebody's going to walk away eventually with the jackpot. But what's happened is they've brought in enough ticket sales that they can pay that jackpot and then still have enough money left over. And then once they pay for the cost of running the game, printing the tickets, having the personnel, etc., the rest of the money is supposed to go to scholarships. So those of you who are on Florida Bright Future scholarships, you can thank the lottery for that. It helps fund the Bright Futures. And that's how they're able to have the money to fund that, is they make sure to not charge the fair price. They make sure their expectation is that they come out positive while you come out on average negative. Some people get lucky and win, so their expectation, that part goes out the window for them, but they were super lucky. These probabilities are insanely out of reach for the average person winning the lottery. It's still fun to play. Still fun to buy a ticket, and on Saturday night, it gives, for only about $1, I can pay to have sweet dreams of what I would do if I won. I have it mapped out. So $1 for some sweet dreams. I don't drink or smoke, so that's what I do. All right. Well, thank you for joining me, and I look forward to seeing you again soon when we start taking data and organizing it so that we can start finding probabilities, more complicated probabilities than what we've been doing. So look forward to that. See you soon.